Hello. In the previous video we looked at the domain of dependence of two numerical methods and the domain of dependence of the continuous linear advection equation. The CFL criterion and the domain of dependence tell us about when a numerical method will definitely be unstable. In this video I will describe Von-Neumann stability analysis, which is used to prove under what conditions a numerical method is stable. So we can assume that the solution of a PDE, numerical solution, at time level n plus 1 can be represented as an amplification factor A multiplied by the solution at time level n. Then if we can represent a solution like this, then the amplification factor will tell us about the stability of the numerical method. If the magnitude of the amplification factor is less than 1, then the solution will be stable and damping. This is for all k, that's for all wave numbers and for all delta x, for all resolutions. If the amplification factor, its magnitude, is equal to 1, then the scheme will be neutrally stable. It won't amplify the solution and it won't make it decay, won't dampen it. If the amplification factor is greater than 1, for any wave number k or for any resolution delta x, then the solution will be unstable, amplifying. And then this magnitude of the amplification factor is, A is assumed to be complex, so the magnitude squared is A multiplied by its complex conjugate. So for linear advection, A will be complex because for advection the solution changes location. So if we're going to represent the solution as by multiplying it by an amplification factor, then this A has to be complex to allow the position of a wave to change location. So how are we going to find this value A? We're going to refer back to Fourier analysis. We know that the solution of a PDE in one spatial dimension can be expressed as the sum of Fourier modes. So we assume that phi is equal to the infinite sum of Fourier coefficients multiplied by Fourier modes. So it's a sum of waves with different wave numbers k. And we're going to consider the stability of the solution for individual wave numbers. We know that the linear advection equation is a linear equation, so if we have one solution, if we have a number of solutions and add them up, take a linear combination, then that will also be a solution. And we're looking at linear finite difference schemes. So again, if we've got take a linear combination of solutions of linear schemes, the resulting solution will also be a solution. So it's valid to consider the solution just of individual wave numbers. We're going to assume that we have a uniform grid, so that x is equal to j multiplied by delta x. So j is the position number in space and delta x is the grid spacing. And we're going to substitute in we're going to now represent phi as phi at position j, time level n, is a to the power n, e to the power I k j delta x. So instead of x here we've got j delta x, and because we're at time level n, and we're assuming that phi n plus 1 is equal to a times phi n, phi at time level n is equal to a to the power n because we've multiplied by a n times. So we substitute this expression for phi into the equation for the linear numerical scheme. And then we rearrange this to give an equation for the amplification factor A, which will be a function of k, delta x and delta t. So let's try this out on forward in time, backward in space scheme. So this is a reminder of the equation for forward in time, backward in space linear advection scheme. We're going to substitute in phi jn is equal to a to the power n, e to the power I k j delta x. I'm going to be working through this and I'd like you to see if you can stay a step ahead, so pause the video if needed, so to see if you can do the next line before I show it. So substituting this into here, we get this equation. The next thing to do is cancel powers a lot of these have got a to the power n, e to the power I, k, j, delta x. So cancel powers of a to the power n, e to the power I, k, j, delta x, and then you can rearrange to find a in terms of the current number c and k delta x. So pause the video and have a go at that. You should get a is equal to 1 minus c times 1 minus e to the power minus I, k delta x. We want to find the magnitude of a, so we need to write this equation down in real and imaginary parts, and then by substituting in e to the power minus I k delta x is equal to cos k delta x minus I sine k delta x, and then take the magnitude of that complex number. So substituting this in, we will get this equation, and then in order to find the magnitude, we multiply a by its complex conjugate and do a lot of bit of manipulation, and we'll find that the magnitude of a squared is equal to this expression here, 1 minus 2c, 1 minus c, 1 minus cos k delta x. So we want to find out for what value of the time step, or for what current number, is this magnitude of the amplification factor less than 1, in order to find out when FTBS is stable. So working from this equation, magnitude of a is less than or equal to 1 when the magnitude of a squared, magnitude squared of a minus 1 is less than or equal to 0. So I subtract 1 from this, and that comes out to be when minus 2c, 1 minus c, 1 minus cos k delta x is less than or equal to 0. And that's when c, 1 minus c, 1 minus cos k delta x is greater than or equal to 0. We know that, so we need to find out when this expression is greater than 0, and this needs to be greater than 0 regardless of k delta x. We can't say that the scheme is only going to be stable for certain wave numbers or certain resolutions. If it's stable for a particular current number, it must be stable for all k delta x. So we know that 1 minus cos k delta x is greater than or equal to 0 for all k delta x. So looking at this equation, we can see that FTBS is stable when c times 1 minus c is greater than 0, which is equivalent to when c is between 0 and 1. So we've proved that forward in time, backward in space is unstable if c is less than 0 or greater than 1. So that is if the velocity is less than 0, or if the time step, u times the time step divided by delta x, is greater than 1. We can't really have a numerical method whose stability is dependent on velocity. So from this we need to define the upwind scheme, which is forward in time, backward in space when the velocity is greater than 0, and forward in time, forward in space when the velocity is less than 0. So the upward scheme is first order accurate in space and time, conditionally stable because the stability depends on the time step, and damping. This amplification factor, if c is between 0 and 1, this amplification factor is going to be less than 1, so it's a damping scheme. So what should A be for real linear advection? Is this damping, the fact that FTBS is, or the upwind scheme is damping, is that a problem? Is that realistic? So we'll consider what the amplification factor should be for real linear advection. We'll consider initial conditions that consist of a single Fourier mode. So phi at time 0 is equal to ak e to the power ikx. And then we know that what the solution at time t should be. From the analytical solution, it's just moved around the domain. We can represent this solution as a factor times e to the power ikx. So we can, knowing this solution, we can work out what the amplification factor would be. So we want this as something multiplied by e to the ikx. So we get this solution is equal to ak, and that factor would be e to the minus ik u delta t times ik delta x. So if we're looking at the amplification factor of the numerical solution, for n time steps, the amplification factor would be e to the power minus ik u delta t. So if t is equal to n times delta t, the amplification factor to the power n would be this, e to the I k u t, and if we split that up, we can split t up into time steps, so then we see that the amplification factor is e to the power minus I k u delta t. This has magnitude of 1, so we can see that under the influence of linear advection, waves should not amplify or decay. So this decay of the upwind scheme is not realistic. I'm now going to show you Von-Neumann stability analysis of the centred in time, centred in space linear advection scheme. So we find the amplification factor A by substituting in phi is equal to a to the power n e to the power I k j delta x into the equation for CTCS. Here is the equation for CTCS. So try and stay one step ahead, try and do these steps before I do, pause the video if necessary, and substitute that into there, which gives this equation. We can now cancel powers of a to the power n e to the power I k j delta x to give this quadratic equation for A. And then we know the solution of a quadratic, so we get A is equal to this complex number with a plus or minus in it. In order to see when this complex number is going to have magnitude less than or equal to 1, there are two cases to consider. First of all, we'll consider the case when the magnitude of the current number C is less than or equal to 1. So if C is less than or equal to 1, this term inside the square root will be positive. This square root will be real. So then we'll have the magnitude of A squared is equal to this number, the complex, the imaginary parts cancel, so we get the magnitude of the amplification factor equals 1. That looks terrific. This is 1 is the right answer. So CTCS is neutrally stable. It doesn't damp the solution, and if the current number is less than 1, it's stable. Fantastic. The solution is stable and not damping. Brilliant. If the current number is greater than 1 in magnitude, then this expression inside the square root can be negative. So the whole of the amplification factor can be imaginary. It won't have a real part for some values of k delta x. So then the magnitude of the amplification factor will be given by this expression. And at least one of these roots, either the plus or the minus, will have the magnitude of the amplification factor greater than 1. So it will be unstable for C greater than 1. So CTCS is conditionally stable, and it's stable for magnitude of C less than 1. However, so it looks great that when it is stable, it's not damping, but there is a problem. We've got always have two possible solutions. We'll always have this plus or minus. So there's going to be a realistic solution, which is called the physical mode, and an unrealistic solution, or an oscillating solution, which is the spurious computational mode. This will contaminate the solution and behave in a realistic way. This is also related. When we looked at the domain of dependence, we could see that the solution, you could have two possible solutions on two different sets of points. That concludes this video on Von-Neumann stability analysis. There are some exercises at the end of the chapter asking you to do Von-Neumann stability analysis on different schemes. There will also be some exercises in the assignment. And the final video on this chapter is about conservation.